time. Good morning, good afternoon, and good evening to everybody around the world. We'd like to thank our tinyML Talk sponsors, Edge Impulse, Maxim Integrated, and Synsense. If you're interested in sponsoring the future tinyML Talks, please contact Betty at tinyml.org. Watch out for our next upcoming tinyML Talk on Tuesday, July 7th. On benchmarking and improving neural network execution on digital signal processor versus custom accelerator for hearing instruments, and how to train and deploy tinyML models for 3 common sensor types by Dan Sitanaike, who is one of our tinyML organizers as well. At the same time, 8 a.m. Pacific. Please contact talks@tinyml.org if you're interested in presenting at a future event. So first up, we have Unmesh Kurup from LG Electronics. Unmesh is a senior manager AI in the advanced AI group in LG Electronics. His focus is on training deployment of machine learning for edge devices. Previously, he was at Robert Bosch Research, where he developed multiple data science projects in energy, healthcare, and ADAS. He has over 20 years experience in AI and ML. Take it away, Unmesh.
Thank you, Ravi. So I'm going to be talking here today about a few different things, but and this is a long title, but the bottom line is that I'm going to introduce 3 techniques that can speed up training of stochastic gradient descent, and that is applications for training on devices, because devices usually have low compute, low memory. You want to speed up training in some way. This work is by a number of people. Samarth and Jason have done the brunt of the work to set up all of these experiments and to actually develop these techniques. I'm just the presenter, but we all work for LG Electronics at their America Research Lab, which is an R&D innovation center here in Santa Clara in California. So anytime I start this talk, I ask this question of the audience: who wants to train a neural network, a deep neural network, on a device? And most of the time, there's only maybe 4 or 5 people who are interested. And I always ask them, what is wrong with you, right? Why are you trying to train a deep neural network on a device? But that's a joke, right? There are lots of reasons why deep neural networks are really popular for a variety of data sets. For example, for anything that's unstructured, for image processing, for object recognition, for audio stuff. And we're seeing more and more deep neural networks actually working on devices, doing inference. So it's only one step from there to actually go from just doing inference to actually doing training. And the reason it's good to do training, there are a lot of reasons, right? There are privacy reasons. There are personalization reasons, because now you can have models that are heavily personalized to each person. But there are also cost reasons. It takes a lot of data transfer to send your models and data back to the cloud. And, computing on the cloud is not cheap. I mean, if you've ever run an AWS GPU instance for a day, you know how expensive it can get, right? The rest of the compute is cheap, but AWS graphics, GPU computes, they're expensive. And I know, because every once in a while, I'll get an email from IT going, what are you doing? Why is it costing so much? So there are lots of reasons why you want to train a deep neural network on a device. And here I'm going to wear my Captain Obvious hat and say, training is expensive, right? And we all know this. And the reason why training is expensive is the best technique we have for training these neural networks, which is stochastic gradient descent, is expensive. It's slow. And it's not surprising, because we are doing optimization on a high dimensional non-convex space. So SGD is slow. And there's a second problem. SGD is volatile. And by volatile, I mean, when you look at this graph, you can see that the blue line is SGD. It's not showing you a nice monotonous monotonic curve. It's actually moving up and down. And that is a problem because one way to make SGD faster, the easiest knob we can turn to make it faster is the learning rate. But the moment you crank up the learning rate, the volatility really goes up. And so this slide is sort of the takeaway slide, in that we're going to talk about techniques where you can turn up the learning rate, making SGD faster and variants of SGD faster. And you can see it in the red curve that we show, which is one of our techniques where you're getting to, I don't know, 90% accuracy on CFAR in about 25 epochs, right? Compared to, what is it, about 80 epochs for SGD. So the whole takeaway from this talk is this, that SGD is slow, and we're going to introduce techniques that are going to speed it up. And the way we speed it up is by reducing the volatility so that we can crank up the learning rate. Now, how do we do this? Whenever you have something that's very volatile, one of the easiest ways to make it better is to, of course, use something like averaging, right? A moving average, a weighted average, they're all techniques that work. And this approach is not new, because if you look at SGD, for example, there are versions of SGD that use some kind of averaging. There is momentum. Atom, even though it uses second order information, is a kind of averaging. But those are averaging approaches that are applied to the gradients. And we want to take a different approach. We want to apply averaging to the weights themselves, the actual weights, not just the gradient updates. That has a long history as well, going all the way back to Polyak-Rupert averaging, which is a kind of averaging from which there are many other versions that people have built. And this chart shows you many different flavors of Polyak-Rupert averaging. And you can see that some of them actually do have show a reduction in volatility, like back epoch and back batch. But all of these techniques have a disadvantage. And that is that they don't perform as well as HDD. And that is a drawback, because we want techniques that, while they're less volatile and faster to train, we also want techniques that are pretty good in giving us the accuracy that we need. So to handle all of these issues and to make SGD faster, we have come up with a technique called periodically sampled weight averaging, or PSWA. And on the left, you can see the algorithm for it. And if you're familiar with SGD, then this algorithm is very similar. The only differences are in steps 6 and 7. I want to take just a moment to show you what the differences are. Step 5 is the normal weight update that you see in every SGD, right? You take the previous weights, you update it with the gradients and multiplied by a learning factor. But in step 6, we do something else. We keep track of the averages of all the weights in every batch, right? We keep a moving average of it. We keep a moving average of it. In step 7, at the end of the epoch, in normal SGD, wherever you end at the previous epoch, that's where you start from. But in periodically sampled weight averaging, we assign the averages of the weights we have calculated back to the weights of the network. And when the next epoch starts, that is where you start from. It's a simple difference, but it has fairly important consequences. If you look on the graphs on the right, now you're seeing a comparison between SGD and our technique for CFAR 10, and this is for ResNet 18. And you can see that these curves are very similar. One is showing the accuracy, the other is showing the loss. You can see how much of a difference just this assignment of averages makes. Now, to make this work, we also, if you're using batch normalization, there is a problem, because the the means and variances that have been calculated are off when you reassign the weights. So we have a recalibration step that happens in step 8. This technique works really well, as you can see, but it has 2 drawbacks. The first one is that keeping an updated mean of the weights is expensive, because now you're doing this additional computation step for every batch for millions of parameters. And the second thing, which is a little hard to see from the graph, is that PSWA, which is our technique, does not give you the same accuracy as SGD. It's very close. It's very, very close, but it's not quite as good. So to fix both of these problems, we started to think about variations on our technique. And one of the first variations we used was, we thought about it and said, do we really need to keep an average of all the weights? Which is very unlikely. So we decided that we would average over some percentage of the samples, not all of them. And in practice, so that means that the amount of weights we average over is, let's say, it's a hyperparameter. But in practice, what we have found is that this hyperparameter, let's call it K, for values between 2 and 5 is sufficient. It performs really well for these values for a variety of tasks.
Unmesh, I have a question for you.
Sorry, yeah.
Sorry to interrupt. Just in terms of what you've been showing, not just the additional computation of calculating the running mean, but if you're memory limited, storing an extra, so many copies of the weights could also be a limiting factor, right?
Exactly, Ravi. Yeah, that's a really good point that I missed. Yeah, when you're storing all of these, that's extra memory that you need as well.
Okay. If you have like a running mean, which is just one snapshot, but with a forgetting factor, rather than carrying the last k different values, would that be a way to reduce? Is that what you do with like a forgetting factor, or do you actually store the last k values, the sets of weights?
We keep a running mean.
Running, okay.
Yeah. Thank you. That was an excellent question, actually. I should have mentioned that earlier. So we have this, we use just the last k samples to calculate the mean. And if you can imagine that when k is 100%, it's basically similar to the previous technique, which is PSWA. So this new technique, we're calling PWalks. And you can see when you compare the curves for PSWA and PWalks with different k values, now you're starting to see that not only are these techniques doing really well initially compared to SGD, but towards the end, they're also getting accuracies that are just as good as SGD, right? So in some cases even better, but not statistically significant. So now we are at a point where we can say, okay, now we're not compromising on accuracy to actually get performance that is in some ways better. And similar to the previous technique, we also developed another technique called periodically sampled weight momentum, where instead of just averaging over the last k% of samples, we're using something that's similar to momentum, right? We're doing an exponential decay of the weight by keeping some percentage of the current weight and then taking some percent of the average from earlier. Again, we find that the decay factor, we call it M, is a hyperparameter, but it works pretty well for a range of values and from the experiments that we have run. And you can see the same effect here. It does really well in terms of having reduced volatility, but at the same time, it performs nearly as well as, or it performs as well as SGD. So at this point, I know what many of you are thinking. All of these experiments that I've shown are with SGD, and nobody really uses SGD anymore, right? So we also ran experiments with momentum, right? Momentum is used, actually. A lot of people use momentum. So, and you can see the results when you compare our techniques against momentum. You see the same improvement in performance when you get to, I don't know, 50, 60%, even 70%. It's doing much better than momentum to get to those early, in those early stages. And even at the end, it's doing really well, right? It's showing you accuracy that is similar to what you would get with SGD with momentum. And that goes for both of the techniques. We've compared this with techniques like Adam. And we see the same thing. Now, Adam is a little less volatile, as you can see from the chart on the left, which is unsurprising because it's using second order information. But the problem with Adam is that when you crank up the learning rate, which is what we have done on the chart on the right, you can see that Adam has sort of very bizarre behavior. The volatility is very high, even though at the end it catches up. So that is a drawback that our techniques don't face. You can crank up the learning rate; they still perform well. They're still mostly monotonic in the way that accuracy increases. We've done a whole lot of tests. We've done tests on different data sets. We have done tests to one of the tests we really wanted to run was to see if you were interested in different accuracy thresholds. Maybe you're not interested in getting to the best accuracy possible, but you are interested in, let's say, 90% accuracy, 95% accuracy. How soon can these techniques get you there compared to something like let's say SGD, right? And you can see that you can, our techniques get there much faster. You can get to CFAR 90% in 22 epochs compared to a baseline of 81. For ImageNet Top 5, you can get to 83 or 66 epochs compared to 69. Or for it to get a 93%, there's an even bigger difference there. We have tried, we've tried to compare these techniques when you use different kinds of learning rates, right? And you can see the differences in accuracy for different learning rates in table 2. Here, SGD, as you can tell, as the learning rate changes, there is our techniques do much better at higher learning rates than SGD. So you're getting like a 3% performance improvement. And then we've also looked at intermediate accuracy improvements. So, excuse me, how much is accuracy improving over the first 30 epochs, for example, right? And this is for ImageNet processing. And you can see that, we're, if you use our techniques, there's a 12% improvement in absolute terms in terms of accuracy. And then we've done some volatility analysis as well to show that our techniques are less volatile. So the bottom line is that given the fact that you can use larger learning rates and that you can get to certain accuracy levels much faster, we believe that these techniques have the potential to actually speed up actual learning and training of deep neural networks on devices. We have also done more tests that are not on these slides, including tests for object recognition. We've done it for object segmentation or scene segmentation. So, and it holds in a variety of areas. While I'm talking about this, I also want to introduce some of the other work that we have been working on in our lab. One of them is Optimizer, which is an open source toolkit for doing model training that is targeted at devices. Currently it's a hyperparameter optimization and training and scaling of model training software. What it gives you is an interface to many different HPO techniques like Spearmint or Hyperband or BOHP, whichever you want to use. By changing just one line of code, you can now switch between all of these techniques. You can also scale your model training from your desktop all the way to AWS without having to worry about taking your code and making it distributed. And in the next half of this year, we have 2 major releases planned that will add model conversion functionality so that you can output your models in ONX format, for example. We'll add quantization and also pruning. So together, quantization and pruning gives us a model compression facility that now you can use Optimizer to target devices as part of your training process. The other piece of software I want to talk about, which still falls under our Optimizer umbrella, but is, I think, a little more relevant to this community, is Model Profiler. And it's a tool for profiling models for on-device deployment. So when you're deploying something on a device, you don't want to deploy the model every single time to understand how it's going to perform on that device. Is it, what is how long is it going to take to perform, let's say, inference? With this open source tool, you can actually run it on your laptop, on your desktop, and it'll give you a result that can help you to make decisions about which models to deploy. And to show you how well that works, I have 3 graphs here, or 6 graphs, and it's hard to read because they're small, but that's okay. What's important is that you can see that the lines are a really good fit. And what we have done here is we have compared the performance of Profiler against 3 different devices, the LG G6 and the Samsung S8, which are both mobile phones, and the Jetson Nano. We have compared the performance against predictions for runtime and memory usage. And in both cases, you can see that the fit is really good, right? So if you try a few different models on Profiler and it tells you that, hey, this model right here, it runs the best, it's very likely that it's going to run the best on that device. So you don't have to deploy all these models to figure that out. In some cases, we can go even further. For models that are very similar, so for example, like versions of MobileNet, right? There's 0.25, 0.5, 0.75, 1, 1.25. In those cases, we can not just, and given a particular device, we're not just saying that which model will be the best. We can actually predict how a model is going to do just from these regression lines. You can predict what the runtime is going to be, what the memory usage is going to be. And we believe that this is very powerful because, yeah, again, it saves you a lot of time when it comes to actually deploying these models. So that's my talk. I'm going to stop here. I think there is enough time for questions. And but first, I want to acknowledge again some of the team members who have done a lot of this work. And I'm open to taking questions now.
Thank you very much, Unmesh. That was very informative. We have a bunch of questions coming up. By the way, audience, you will have a poll that pops up on your screen shortly. Please do answer those 2 questions. Unmesh, so one of the first questions that come up is this available to try out in TensorFlow or PyTorch?
It's a very good question. So I think the paper is out on arXiv, but the actual code is not, but it will be soon. I think in the next month or so, it should be out there. We just have to go through our open sourcing process first. Excellent,
excellent. So you mentioned that this is useful for edge, training on the edge, right? Does it generalize to larger networks, or is it particular to, are the optimizations here particular to low power edge networks, like smaller networks, or does it generalize to larger networks?
I think it does generalize to larger networks, yeah. We have, I mean, at least in terms of the actual deep neural networks itself, we have tried it on a variety of networks, from small ones like ResNet 18 to ResNet 50. We've tried it on Inception. So that variety exists, and we have tried it, and this holds. So we believe it's transferable.
Okay. Have you tried it on like the more recent, like MobileNet version 3 or EfficientNet kind of models?
We have not. Mm-hmm. Yeah, definitely not on EfficientNet. MobileNet, I have to check. It's okay. Possible we might have.
Okay. Yeah, that'll be interesting to see how how it generalizes. A question is about, when does it not do as well as SGD or momentum? Have you seen specific cases where it falls short of that?
Right. So The place where it falls short is that we need two of these techniques to cover the full spectrum of SGD in the following way. That first technique I talked about, it's really good. It's really good at not being volatile and getting to 90% really quickly, but it cannot match SGD's accuracy, right? There's always a little bit of fall off. And the other two techniques, they can match SGD's accuracy, but you pay a little price for that. They're still better than SGD in terms of volatility, but not as good as the first technique. So in practice, what we have found is combinations of these two techniques work really well. And that is the drawback, because now you're using two techniques, right? If you want to like really get the best performance in terms of accuracy and speed up, you have to use these two techniques, and that's the drawback.
Right, that makes sense, because there's rarely a single magic bullet that solves everything.
Right, exactly.
Yeah. Another question is about the effect of batch size on the performance of these approaches, especially in edge use cases where you may be really operating at a batch size of 1.
Yeah, so when I started this talk, I had that realization that that's one thing we have not tried it on. Like, what happens when you use these techniques for batch sizes of 1? And I suspect that with batch sizes of 1, now you're performing these computations a lot more times, right? So that first technique I talked about is going to become really expensive. And we're going to have to do some kind of either an exponential decay or some K% of the samples. And those two techniques should still work reasonably well in those cases.
Right, excellent. There is a technique also called like stochastic weight averaging in TensorFlow and PyTorch. Is that related to the initial SWA that you talked about, or is it slightly different?
That I don't know.
Okay.
I have to, but I'll make a note to check it out.
Sure, we can follow up on the forums for sure.
Right.
Another question is about use cases. So other than federated learning and personalization, what other scenarios do you envision that training on edge devices will be useful for?
I think it's, so personalization and privacy security, yeah, obviously, those are the standard ones, right? But cost is more and more, it's going to be a major factor, because the more devices you have, the more data you send back, the more it's going to cost to compute it on the cloud. And if you can do some of these personalization model adaptation on the device, right, you're saving a lot of cost. You're saving bandwidth costs, you're saving cloud compute costs, and you're pushing those costs to the customer who already has this device that they're not using completely all of the time. I think that is going to be a major difference.
Absolutely, I totally agree with that. I mean, privacy, of course, is paramount everywhere right now. But you're right. I mean, we have this free compute sitting around, and if it's not really being used all the time, it might as well be leveraged as millions of distributed tiny computers everywhere.
Exactly.
Rather than training on AWS, expensive.
Right. And something that's very important in this area is also fog computing, right? When you have all these devices at home that you can utilize to do some of these computations, it doesn't have to be your watch or your, a phone. It can be your, let's say, your NAS that is just lying around with a lot of compute.
Yeah, and for different people, different things mean edge, right? Like your router can be basically doing some computation common to all the devices in your home. Like if you have a bunch of smart assistants, your router can do this and redistribute.
Absolutely.
Another question about quantization, whether this works, whether you can use this to compress models and speed up models for edge cases beyond like quantization techniques after this training. Like how does that interplay with here, and how does it impact accuracy?
So that's something we haven't tried yet. What happens when you add quantization onto these techniques? And my best guess is yes, you will still get the speed up from quantization that you're already getting, because quantization affects the final inference speed, while we're talking about improving training and increasing training. So I don't think there is, they're independent of each other.
Okay. A final question, because we're coming up to the half-an-hour mark. In terms of accuracy, you've shown that PWalk is able to really catch up to SGD very quickly and much more stable. In terms of performance cost, which is basically about, in terms of the extra operations that you're doing with the averaging process, how much of an overhead do you see in terms of the flop count? For example, is it like 1% or 10%?
So I think from our experiments, it's about 2 or 3%, but don't quote me on that. I'm not sure. It's something I have to go back and check.
Sure, and I guess it also depends on how frequently you're doing the averaging, because you do have a parameter that controls that.
Yes.
All right. Thank you very much again, Unmesh. This was a very interesting and informative talk.
Thank you, Ravi, and thank you also to the entire tinyML team for putting together these series of conferences.
Thank you. Thanks again to our tinyML talk sponsors, Edge Impulse, Maxim Integrated, and SynSense. Edge Impulse provides a developer platform for ultra-low power machine learning from design to deployment at scale. Please visit edgeimpulse.com for a free developer account. Maxim Integrated, enabling edge intelligence through sensors and signal conditioning, a low power Cortex M4 micros, and coming soon, advanced AI acceleration. And finally, SynSense. SynSense provides dedicated mixed signal neuromorphic processors with an unprecedented combination of ultra low power consumption and low latency performance. Just a reminder for our next tinyML talk coming up on Tuesday, July 7th, same time. Thank you very much, everyone, and see you next time.